like the end-all be-all most exciting way to do this, but it is a way to do it, and it is a fairly efficient way. Did I give you guys enough of them? Okay, I thought so. Okay, good. All right. So I like to do this as a lab, but we do not have the interface to do it well. And again, just kind of trying to pay attention to time and maximize our efficiency. We're going to do this as a thought experiment as opposed to an actual physical experiment. We're going to employ everybody's favorite, whatever, cartoon third grader, whatever grade he's in. I don't remember anymore. Does anybody know what grade Bart Simpson's in and has been for the last decade and a half or two? I don't know. Anyway. So Bart Simpson happens to be, just like everybody else, on a day that he has nothing else to do, standing in an elevator and standing on a bathroom scale. That's my favorite pastime. That's what I thought, and that's why I thought this would make sense and resonate with you all. So anyway, he's in an elevator. It's a glass elevator so we can see in, standing on the bathroom scale that's there, and he's just like, hey, how's it going? All right. So the first thing that we're going to do, we're just going to kind of follow through these 4 steps in order to get us to a decent understanding of what it means to be weightless. So the first situation that we've got here is one in which he is standing still, sitting still, nothing is moving. So the first task says to draw arrows indicating the size and direction of the forces acting on Bart. So this is simple, friends. It's as if he's not on the elevator. What forces are acting on Bart Simpson? Gravity, the force of the earth, pulling which way? Straight down. I'm going to go ahead and write it as FG because I'm just trying to go fast. Okay? And are there any other forces acting on Bart Simpson? Oh, normal force. The normal force. It's really the force of the what? What is he standing on? The scale. The scale. So it's the scale for, I'm going to write this as F sub S for the force of the scale. Okay? We talked yesterday about how this is how one measures your weight, right? You don't actually measure the force of gravity. In order to measure your weight, you stand on a scale, and the scale, whether it's an electronic scale or a spring scale, if you stand on like the old school bathroom scales that have the dial, it's just had a spring in it that's calibrated such that it turns this way to make the thing change, okay? In any of those cases, we're measuring FS. We just happen to know that we're sitting still. Okay, so we're looking at all of the standing still business. So step 2 says to determine the net force that Bart experiences. Is it 0, positive, or negative? I should change it to positive, 0, or negative. Tell me about the net force acting on Bart right now. It's 0. How do we know? Because he's still. He's standing still, which means he's? Not accelerating. Boom, there you go. All right. I want to know, so the reason I left this row in here is because it's got a term that I want you to be familiar with. And that term is gravitational field. It's going to come up again later today, and I want to make sure that you're aware of it. The Earth's gravitational field is really just how much the Earth is putting into the force. Remember that when we calculate FG, we take what times what? Mass times that little g, right? And that little g is true just for Earth. If you were going to go stand on the bathroom scale on the moon, another favorite pastime, then this picture is going to look the same, but your values are not going to be the same, right? And the reason for that is because the strength of the moon's gravitational field is different than that of the Earth's gravitational field. The Earth's gravitational field is the acceleration due to gravity. That's really what it is when we're talking about gravity. So I'm going to go ahead and write that down, and you should too. And what acceleration due to gravity is Bart experiencing here, friends? Negative 9.8, right? Oops, I was going to write this in pink to stay consistent in my colors. All right. And then my last question for you is, for this standing still one, what is Bart's weight? What is the force due to gravity acting on Bart, or what is the scale reading? Can you figure that out? 65 times Should we use the easy one? Should we make it 10? Gunnar wants it to be 10. If you want it to be 9.8, then multiply by 9.8. I'm going to take the easy way. Remember, and friendly reminder that on the AP exam, you can just use 10. You can just say G equals 10, boom, you're done. Makes life easy, just saying. So if I'm going to take that approach, then I know that the scale reading, F sub S, is equal to, that's going to be 650 newtons. Okay? How are we doing, team? That's FS. FS. And that's an equal sign. My stylus was just being silly and funny. I'm sorry. FS equals 650 newtons. Okay? All right, let's do this one. Moving up with a constant velocity. That's the second one in our game. Go ahead and talk to your table real quick. What forces are acting?
And force and scale. He's moving up with ball.
All right. How many forces have you got, friends?
2.
2. What are they?
Force Earth. Force.
Yeah? What's the net force acting on him?
0.
How do you know?
He's moving at constant velocity.
Constant velocity, not accelerating. Awesome. What's the gravitational field acting on Bart? Negative 9.8 meters per second squared, right? Okay. And what's Bart's weight? Bart's apparent weight, according to this right now? 650 newtons, right? When you talk about the weight, we usually don't include the negative sign, just because the negative is the indication of direction. And generally, when we talk about weight, we're just talking about the scalar of the value, not the negative. I'm not going to say it's wrong. I'm just letting you know that we don't need to say that every time. So that's a key there. And I'm going to leave that there. And then we're going to go to the next one because we can. All right. So now the elevator is accelerating upward. It's accelerating upward at 1.2 meters per second squared. Okay? And I didn't really know when I was drawing this how to indicate that it was going upward, except to put little rockets on the bottom, because that means that it's going up, right? I mean, you get the idea. So what I need now is for you to draw the forces acting on Bart. Go ahead and draw the forces acting on Bart. What forces have you got?
Yeah, 2.
You have 2? What are they?
Force of the Earth.
Force of the Earth, Fg.
Force of light scale.
Force of the scale, which now goes up. Okay. Anything else acting on Bart? Nope, that's it. What's his net force? Is it positive, 0, or negative? It's positive now, isn't it? Because he's accelerating. He's accelerating the upwards direction. So we've got a positive acceleration. Tell me about the strength of the Earth's gravitational field. Has it changed?
Still 9.8.
Okay. It's still 9.8. And I want to make sure that you're seeing that because it's going to matter as we move over here. Tell me what the scale reads. Is it 650 now?
No.
No? Do you need a second to figure it out? Do it. You can do this. You absolutely have the capability to do it. I'd write out an F-net equation. That's what I would do. That's what I did. When in doubt, if you have a free body diagram, F-net equation is the way to go, friends. Fantastic. So you wrote down some sort of F-net equation here probably, right? I hope so. Just because it's always a good idea. Thank you. What forces do you have acting? Fs and Fg. And those equal Ma. Right? And so from that, we can calculate that Fs. Oh, we have to note that things are going in different directions, huh? Like the force of the scale is going up, the force of gravity is going down, the force of the net force is going, what did we just say? Up. So that's going to be positive. So when I move FG over here, then what's going to happen? I'm going to have to add this, right? So Fs is really equal to Ma plus Mg. So it's going to be whatever 665 times 1.2 is, plus the 650. What do we get for a number? For a value there? If you don't have a calculator out yet, you will need one today, I promise, because we're going to do a bunch of calculations in a little bit. So go ahead and get it out now because you'll need it.
Do you know, Ms. Carbley, do you know any science teachers that spray their calculators orange and math teachers?
I, not here, but I do, and I'm planning to this summer.
Oh, you don't? No, this was my sister's.
Oh, but that orange one, I don't know who's that.
My sister definitely took it from a teacher.
Definitely.
Yeah.
I don't know who, though. I'll ask around. How long have you had that calculator?
Teacher.
4 years.
Definitely Mr. Lefty's calculator.
I didn't steal it.
All right. What do we get for a value, friends? 728? Okay. If you use the 9.8, I think when I did it before, I got like 715, something like that. Either way, here's the thing that I want you to notice, is that by just standing on a bathroom scale in an elevator, that's all he did. While going up, he's apparently gained weight, right? Yeah, so he's, in big quotes, gained weight. And by that I mean the scale reading has gone up. I'm going to change this weight to apparent weight. Okay, just to be really clear. All right. Let's find out what happens when he goes down. Accelerating downwards. What forces are acting? Same thing. Right? Patterns emerge. So FG is going down. FA is going, or FS is going up. The net force is now in what direction? It's in the negative direction. Has the gravitational field of the Earth changed? It has not. It is the same thing. Tell me what the scale reads now. You can probably make a prediction as to whether it's 650 more or less. Okay? Same game that we did before. This is a nice review of the things that we did so long ago in September or October. The scale force is positive, gravity is negative, and oh my gosh, the acceleration is negative as well. Okay, are we good? Yeah.
Yeah.
Okay, I just want to make sure I wasn't like upsetting anybody there. So 65 times negative 1.2 plus 9.8, or you could use 10 there. How much does Bart weigh now? Or what is his apparent weight?
572 newtons.
572 newtons? So, oh my gosh, by just being on a bathroom scale and accelerating down, he's apparently lost weight. Are you with me there? Easiest way to lose weight, if you will, or gain weight. I don't know if there are any wrestlers in here, but right, if you have to like make weight, just figure out how fast you'd be going in the elevator when you measure it. Maybe that's the best way to do it, right? Okay. Okay. Now, I like Bart Simpson as much as the next person. And I'm not like trying to make him meet his demise. But I want to look at this very last situation. Look what happened to that cable above him that was holding him still. Or pulling him up or pulling him down, right? Yeah, all of those catchphrases from the early Bart Simpson days. He is now in free fall. If you've never heard that word before, we need to meet it now. Oh my gosh. What does free fall mean?
There's nothing.
There's no gravity.
No normal force. The opposite.
I'm not going to point out who said it, but I really need to point out. And the whole reason that we spent 25 minutes on this is to point out to you, is there gravity in this situation?
Yes.
Nothing else has changed except that the cord has broken. The acceleration due to gravity is still -9.8, right? It is still the same thing it was before. This is here. It's still there. Okay? Gravity still exists. To be in free fall only means that that's the only force acting on you. To be in free fall means that the force of gravity is the only force acting. Well, that makes drawing a free body diagram pretty easy, right? Since I just told you what it was. How many forces are acting on Bart right now? Just one. And what force is it? The force of gravity, right? Now, I put the scale over here just to kind of like give you that image, but he might still be standing on the scale. But is the scale pushing back on him? It's not. The reason in every single one of these other pictures that the scale was pushing back on him was because the floor was pushing on the scale. We could go through the same process here, drawing the free body diagram of the scale. It would be that would be Bart pushing down, be the floor pushing up, right? Like we get that whole thing? Yeah, and then gravity too, blah, blah, blah. But you see what I'm saying? Here, the only thing pushing on the scale is gravity as well. What's the net force? Is it positive, zero, or negative in this case? There's only one force, and that force is pulling down. So it's got to be negative. We just said that the gravitational field is still the same. But if we think about it, if the scale is not pushing up at all, what is that scale going to read, friends?
0.
It's going to read 0. It's going to read 0. This is the situation where Bart is weightless. Okay? This is weightlessness. If you have ever been on is it the space shot? Is that what they call it at Adventureland?
Yeah.
The one that takes you up really, really high, and you can see out everywhere, and then it drops you. During that, just the very, very beginning of that fall, you experience weightlessness. I don't know if it happens to you or not. It really depends on how big you are relative to and how well the harness is over your body. But I know that when I was a little kid, I would sit on that, and my butt would come up off the seat as the seat was falling, and I was falling, right? You with me there? That time right there, I was experiencing weightlessness because there was nothing pushing back up on me. So if I was sitting on a little tiny bathroom scale, okay, that bathroom scale just for a moment would read 0. Okay? When astronauts are in space and they're orbiting the Earth, they experience weightlessness. Is there gravity?
Yes.
Absolutely. Absolutely. The reason that they are weightless is because their whole ship, whether they're on the space station or whether they're on a shuttle or whatever it is falling just like they are falling, just like everything in it is falling, and because everything is falling because of gravity, they experience weightlessness. Weightlessness does not equal no gravity. Remember we said yesterday that the gravitational force is infinitely, like it lasts forever. So you can't get anywhere with no gravity. But you can absolutely experience weightlessness without a whole lot of effort, honestly. Okay? We doing all right? Questions right now? Okay. We are going to have an opportunity right now. I'm super excited to do, you guys know who my least favorite scientist is, right?
Yeah.
Einstein.
And people talk about how great and brilliant he was. We're going to do everything that he is super famous for right now today. Are you ready? Let's do it. We're not going to do the calculus part. No time for that. No, decidedly not. All right. So, you might want to use on separate paper. You could do it on the back of that yellow piece of paper if you wanted, although mine took more than one page. So depending on how big you write and all of that sort of thing, we are going to, right now today, in the next 20 minutes, derive the universal law of gravitation. Here it comes. Let's do it. Let's do it. All right.
Oh, the jacket's coming on.
I know, right? It's going to be good. I got to go fast. We got to, here we go. All right. So we talked a little bit, this was a really nice segue between the weightlessness thing and the universal law of gravitation, because we're really talking about things that are falling, okay? The story goes that Isaac Newton, this was, during the time of the plague, he went home to his mother's house and he was just hanging out, trying not to get sick, sat under a tree, and what fell on his head?
An apple.
An apple, and he said, oh, gravity, and before that, nobody knew that gravity, everybody knew gravity was there, right? Like, it's not a surprise. The story goes that he invented gravity, but that's completely bogus. The thing that is important, the connection that he made that no one else had articulated, at least before, okay, was the idea that just like the apple falls, the moon falls as well. So let me tell you what I mean by that. There's a very, very famous book that he wrote, and in that famous book, he drew this famous picture. So there's the Earth, and on that picture, or on that Earth, there's a mountain, not drawn to scale. And this was the thought that he had. This is the idea that he had. He said, okay, I'm going to take a cannonball, or I'm going to take an apple, or I'm going to take a whatever, and I'm going to throw it. And as I throw that ball, what's it going to do? It's going to fall, right? A little projectile motion. Okay? Now I'm going to take that apple or that cannonball or that whatever, and I'm going to throw it a little bit harder. What's going to happen to it? It's going to go further. We did this before. This is just projectile motion, right? He was not the first person to figure this out. I want to make that very clear. So I'm going to throw it a little bit harder. Here it goes. It's going to fall down. Okay? I'm going to throw it a little bit harder. What's going to happen to it?
Falls off the earth.
Oh my gosh, it's going to fall off the earth? What does that mean? It means that it's going to go. And as it falls, the earth is now there's no earth for it to fall onto. So it's just going to keep going around and around and around and around. And I'm not going to draw this well because, my circles are not the best. But you get the idea. And it's just going to keep falling, because why wouldn't it keep falling? Right? Because if you draw the force on any of these, you guys drew all these forces before, all of them are experiencing a force which way? Down, towards the center of the earth. Right? So it's going down, it's going down, it's going down. That's what it's going to do. The force is going to the center of the earth. It's like that circular motion stuff. That's why we're doing this right now. Are you with me here? Yeah? This is all circular motion, friends. It's going to keep going around and around and around. Oops, my stylus says no thank you. I say yes, please. And the person that threw that thing, if they have a really good arm, needs to duck. Yeah? Because it's going to come back and hit him in the back of the head. Now, if we're clever about this, then we can do the same thing with anything. We could launch it up a little bit and then get it to go, and it's just going to fall. And it's going to fall and it's going to orbit. That's exactly what an orbit is. Okay? So what Isaac Newton thought was, maybe the same darn thing is happening spinning to the moon. So if we zoom out a little bit and we put the moon out here, here it is, and it's just falling. It's doing the same thing. So it's just going to fall and it's going to go in this orbit. Okay? The moon is falling, and that's why it orbits us. We fall around the sun. That's why we're in orbit. The sun falls around the center of the Milky Way galaxy. That's why we're in orbit. That's all it is. Okay? All that an orbit is an object falling, but it's got some tangential velocity. That's it. Okay? So that was kind of the big deal realization. Okay? So now, no. You're on your way. You have dipped your toe into. Okay? So the idea, is that the moon, which is orbiting the Earth, is falling toward the Earth, right? And he's done this math just like we've done this math. And we can take our frog and we can drop it, and he did the same thing. And I can measure how fast the frog falls. I can measure the acceleration due to gravity, right? And so that's all well and good. So we're going to do the same thing. So now my question is, I've got 3 big questions to ask today, okay? Question number 1. This one you can solve all by yourself. How far will the moon fall in one day? Okay. 1 day is 24 hours. Yes, good call. And that's not a trivial statement, because if you don't get that, you're just gonna be in trouble, right? This is 24 hours. You may need to convert that to something other than hours. So here's my deal. I can tell you how far the frog can fall in 0.2 seconds, right? Sure. I can calculate it so I can figure it out. I want you to, so we're going to do that. I want you to figure out for me how far the moon is going to fall in a day, because the moon just keeps falling and falling and falling. I want to know how far it's going to go in one day. Can you do that for me?
What's the radius of the Earth? It's like 6,200.
Let's back up. How far will the frog fall in 0.2 seconds? Can you do that problem?
Yes.
Do you need the frog's mass? Do you need the radius of the Earth or the radius of the frog? And I don't mean this to be a smart aleck. I mean this, I want you to think about it before you start asking for details. You can figure out how far the frog falls in 0.2 seconds, right? I want to know, put the frog up there. Sure, that's fine. How far will the frog fall in one day? If he was left to fall for a whole day, how far is he going to fall? Can you do that? Yes, Miss Carlin, I can. Find an equation. Write down your givens. You know this. What's the initial velocity? What's the time?
24 hours.
24 hours, but you got to convert that into seconds. Hours. What's the acceleration? Negative 9.8, right? I want to know dy. That's all I'm doing. You can do that. The distance it's going to fall down, right? Do it. Figure out how far it's going to fall. Everybody's doing this. You got your calculator out. I told you you needed it today. Get out a calculator and figure out how far it's going to fall. Just do it. Just do it. This is the purpose of this.
Remember what they said, if you had a job every second in the day. So put it in the bank.
1 day in seconds squared. 3,600 times
So it's like,
24
you had a job every single day. Would you put
7.
it in the
That's a
bank?
big number.
Which equation are we using?
It's such a big number.
Yeah.
That's my favorite.
Yeah, mine too.
So,
Use it all up in it. Then you don't get money that's left over.
This is just good kinematics, right? We can do this. How far does the moon fall in one day?
10 to the 10th power.
36 billion meters.
3.66 times 10 to the 10. Is this?
Does anybody know how far it is between the Earth and the moon?
16,430 kilometers.
The distance between the Earth and the moon is 4 times 10 to the 8th meters. I want to make sure I have that right.
So you got right.
I think that's right. Somebody double check that. I just can't read my notes. Can somebody just look that up on their phone real quick? Distance between the moon and the Earth. Who's got that? All right. I'm pretty sure that's true. All right. How are we doing here? Do we have some problems? Anybody confused or unhappy? The distance between the moon and the Earth is 4 times 10 to the 8th meters.
Yeah, that's not that far.
Kind of.
That's a lot of zeros off. Orders of magnitude off. This is saying that if the moon falls for a whole day, it's going to go towards the Earth and pass it. Does that happen? No. So there's a problem there, right? There's a problem. There's some assumption that we made that is incorrect. What's the assumption that we made that's incorrect? It's this one. It's this one. This is the piece. It came back from the weightlessness. It came back from the strength of the Earth's gravitational field. We need to figure out what that means. So, we need to ask question number 2. And question number 2 is, how far does the moon fall in 24 hours? And Courtney says what? That's the same question we just asked. I know. We're going to solve it a different way this time. Okay? Instead of just doing what we did and make an assumption about our acceleration, we're going to do a little bit of thinking. I know. It's kind of amazing to think about that. Go ahead and draw yourself a picture with me. Here's the Earth. Not at all drawn to scale, but we're just getting a sense of what's going on here. And here is the moon. The moon is out some distance here. And we know that that distance, did somebody double check that number for me? Okay. Okay, awesome. Thanks. This is the distance between the moon and the Earth. Okay? So center to center. I'm just saying the distance from the moon to the Earth. Now, we know, we think, we understand that the moon is going around in a circle, right? It's an orbit. It's a nice, pretty circle. So if we imagine that, if gravity wasn't there to pull on the moon, where would the moon go? Think back to that yo-yo. Think back to all that circular motion stuff we did. Which way is it going to go? It's going to go in a straight line, right? So if my orbit is going like this, in this direction, if I don't have the Earth pulling in on the moon, then the moon is going to go in a straight line tangent with that radius. Are you with me there? But instead, that's not really what happens, because the moon actually, I'm going to try and draw this. I always struggle with this one. I'm going to do my best here. Like this. This is not, obviously, again, not drawn to scale. Okay? Because we're going. Oops. This is its tangential trajectory. So instead of following this tangential trajectory for 24 hours, the moon actually falls a little bit, doesn't it? But it doesn't fall a really long way. It just falls this far. I want to know this distance here. How far is that falling? How far is that little distance? I'm going to call this delta x. That's the little piece. That's what I want to know. Now, it might look kind of intimidating to you, so I'm going to help you out to figure out how to do this. Here's the nice thing about all of this, friends. You got a nice right triangle here. See that nice right triangle? with this little right angle here? The right angle between the tangential velocity and the radius? This is your hypotenuse. And the difference in length between your hypotenuse and the distance between the moon and the earth is how far it falls. The reason we're doing this, let me back it up to tell you why we're doing this. Once we find how far it falls, we can determine the acceleration at the distance or the location of the moon. So we're working back with one data point because that's what we got. Because we didn't have lots of satellites out there because we didn't know any of the stuff to get the satellites out there, right? So we're going to try and figure it out with one data point. How far does the moon fall in 24 hours? You have, I think, all of the information you need. I think, unless there's something else you can think of that you might need from me. Anything else you might need from me? The distance between the moon and the earth? Is 4 times 10 to the 8th. In order to figure this out, you probably need to know how far it would go in 24 hours, which probably means you need to know some sort of velocity. How are you going to figure out the velocity of the moon? What kind of a shape does the moon travel in?
Spherical.
Wrong answer. Try again. It's a circle, right? Yeah, nice job. How long does it take the moon to go around a whole time around the earth? Do you know?
A month.
A month. 28 days.
A lunar cycle.
Yeah.
That's why you can
All right. You have everything you need to know. Before the bell rings, I want to know how far it falls. I want you to figure it out, you guys. I'm not going to do it for you. This is physics that you know how to do. Figure it out. How far does the moon fall in 24 hours?
Exactly what I had. Yeah.
All right. So, friends, just to be clear, because the bell's going to ring quick and I want to make sure that we're okay, we're going to jump in here in just a minute. Stay with me for just a couple seconds here. So you're using the velocity of the moon to figure out how far the moon would go without any gravity. You've got one side, you've got another side, 2 legs of a right triangle. So you can figure out the hypotenuse of this triangle. And from that, you can subtract that to find delta x. For delta x, I got, when I did this a while ago, let me see, I got, make sure that I'm looking at this right, 1.0 times 10 to the 7th. For delta x.
Wait, so hold on, I got the hypotenuse. What do you do when you get the hypotenuse?
Subtract the hypotenuse from DME, because this distance here to here is DME, and then this is how much it's falling. Yep. Tomorrow we will finish. Be well, my friends.